Okay, hello everybody. So actually there was a talk one session ago which had the title Immutable Data Structures and then was about something completely different. This talk is actually about immutable data structures. In particular, it's about a data structure I implemented in the context of space mission planning for sets of non-overlapping intervals. So about me, I'm a software engineer at Actix, and we are trying to bring modern digital technology to manufacturing. I previously worked in space operations at German Space Operations Center, and there I did space mission planning using a Scala library called Spire, and I did telemetry, display, and archival using akka, which I think some people might know. So I contributed to the Scala 2.11 collections library, and I'm still contributing to the Spire math library, which is a Scala math library. And in particular, I have improved the performance of the rational number type, and I've implemented these two data structures called interval seek and interval tree. And this is basically what this talk is about. What's this talk about? It's two different data structures, one tree-based, one array-based, to represent sets of non-overlapping intervals and to perform operations on that. We got a tree-based data structure. First of all, this is a Java Scala world, so we have basically primitive types, which can be bytes up to floats and doubles. And then we have other types which are composed of these primitive types. And so there is a tree-based data structure, which is for data types up to long, basically everything that fits into 64 bits. And then there's an array-based data structure for any type for which you can define a total order, meaning you have some way to compare the elements which obeys the laws for ordering. So obviously, the one thing is way more generic because there's way more types for which you can define an order than types which fit into 64-bit. But the other one, as we'll see, has some performance advantages. That's one thing that is quite a bit better than other libraries that have already been existing. They both very efficiently support Boolean operations, these data structures. And they are both included in an open source library, so if you're a Scala developer, you can just use them. And I might at some point actually port them to JavaScript to have more people to reach that, but currently it's only reachable from Scala or Java. So let's have a quick overview about what are mathematical intervals. So mathematical intervals are a little bit more complex than just having a start and an end. You can have, for example, intervals which start from a certain point and go up to infinity. Well, infinity is not actually a value, but it's a concept. But basically, you can have an interval that does not ever end. You can also have intervals that start from negative infinity, or you can have the interval. This is the interval that contains every single value of the type for which you have defined it. So we will see how these are useful, but first of all, let's see what is there. Next thing is mathematical intervals keep track of whether the boundaries are included or excluded. So in this case, 0 is included, 10 is included, and in this case, 0 is excluded. So the value immediately above 0 is included, but 0 is not included. Same with 1. And another thing that we want, which is a bit more difficult than just having start and end point, is we want the ability to represent single points. So this would be just the point 10, just the value 10, and anything immediately before or immediately after would no longer be included. And also it's quite helpful to have the ability to represent the empty interval, so no values match this interval. So that's mathematical intervals. Now let's take a look what they're useful for. I'll try to motivate why they're actually useful in the real world. So what's this good for? It's a good question. One example might be a very simple example, calendar scheduling. So let's say you got this situation. You got a huge team and you got lots of colleagues, and you want to figure out when to do a meeting. Maybe you're the guy that's implementing Google Calendar or whatever. There you have the situation, for example, you have 3 employees, 3 developers, and the times in which a developer is available can be represented as multiple intervals. So one is working from 9 to 5, so every day in the week from 9 to 5. The other one works maybe in California, so in our time zone he has different intervals, and then you want to find at least one place where you can schedule a meeting. So yeah, let's say our employees are gender neutral A, B, and C, and I want to show that mathematical intervals are actually useful to represent real world concepts. So, for example, an employee that does not have any constraints whatsoever. So he's the poor DevOps guy that gets called in the middle of the night and has to answer the phone. So he is basically that guy. And then you might want to limit your solution space to only values which are in the future, because you're not interested in meetings in the past, basically. Then you could just represent this constraint as an interval from the current time to plus infinity. Or you might say, I want to do my meeting at least in the next month. If I can't do it in the next month, there's no point anymore. In that case, you would basically, in mission planning speak, that's called a planning horizon. You would say, I want only the interval from the beginning of time until next month. And then you would you could use that to exclude all solutions which are outside the planning horizon. So another example might be, you might not want to have meetings on weekends, so you could have an interval that goes from Saturday to Sunday. Obviously, these are dates, but I just wrote the names. And then you can negate it, which means you get everything except that time period. And when obviously, sometimes you are not able to find a solution. And in that case, you need the ability to represent the fact that you didn't find a solution. And that's what the empty interval is for. So if you perform an operation and the result is the empty interval, you know you didn't find a solution. Okay, so this is actually what I implement this for. This is a mission, 2 satellites that fly around the Earth and create a digital elevation map. And it's actually in space right now. The digital elevation map is completed. And we will see that in that pretty much more complex domain, you'll have the exact same problems than in the simple example of calendar scheduling. So when should activities on spacecraft happen? As an activity would be something called a data take, which is taking a picture, basically, in a very simple way. So every single thing that happens on spacecraft can produce a constraint. For example, there are power constraints. Very simple. If you don't have the power to operate your camera, you should not take a picture. So that gives you a set of intervals where it's not possible to do the operation. Next thing, you have thermal constraints. That's a bit more weird. The instrument can get hot when you operate it continuously for a long time. And when that happens, it breaks, which is a bad day, really. So you have certain intervals in which you should not switch on the instrument. That again gives you arrays of intervals that are excluded or included when you negate it. Then you got data constraints. It's also very obvious if you think about it. If you don't have space to store the image, there's no point of taking the image. I mean, you can do it, but you have to throw away the data, so there's no point. And next thing is there's geometric constraints. Sounds very fancy, but it actually just means you should only take the picture when you're over the target. So when you're not over the target, you're not going to get a good picture. Okay, so as you can see, this is a completely different and way more complex domain, but it's the same things that you can do. You can operate on sets of non-overlapping intervals. So another example would be production planning, which is more like what I'm currently involved with. But I think now that we've seen that this would actually be useful, let's take a look how we would implement this. And being a good software developer, the first thing you would do would be something very simple. So let's see how the two possible solutions could look like. One thing, this is going to be functional data structures. I'm going to explain why. First of all, are mutable data structures faster? I got some very impressive benchmarks to show that it is not the case, actually, in this particular case. Next thing is automatic scheduling. What you do for the space mission planning domain involves exploring multiple solutions. So basically, you have a big data structure. You make a small change. You check whether the small change has improved things or not. And if it has improved things, you keep it. And if it has not improved things, you throw it away and just try something else, basically. Very simple, in principle. And this is called backtracking. And if you have functional data structures, obviously you don't have to do anything to undo the changes when you want to basically not explore a certain solution anymore. So you just have a pointer to something that you don't need anymore, you just throw it away and the garbage collector takes care of the rest. So that's what I call backtracking for free due to structural sharing. Obviously it's not free, the garbage collector is not free, but it's pretty fast. And that's another thing which is probably even more important than all the developer advantages that we like. Functional programming allows a programming model that is safe for planning domain experts. So the planning domain experts are mathematicians, basically. And they really don't want to do, what they really don't want to do is chase memory holes or pointers in C++ applications. So using functional data structures, you can write a domain model which allows the domain expert, a mathematician, to concentrate on the actual important thing, which is finding a good solution and not chasing memory leaks and pointers and so on. So actually, the prospect of having these people working with mutability kind of scared me, and it worked out pretty well. So okay, so that's why we're using functional data structures. Okay, now we get to the two different approaches. As I said, the first approach is the most dumb, stupid thing you could possibly think of, which is let's say you have this. This is a interval set, a set of non-overlapping intervals containing 3 intervals. And so how would you represent this? Well, the simplest thing you could do is, let's first take a look what we need to store. So obviously, it's completely obvious that we need to store the places where something happens. So we need to store these numbers somewhere. It might be a different data type, then it would be different numbers, but these numbers, they need to go somewhere. There's no way around it. So basically, we need to store where something happens, and we can store that basically in a sorted array. And then next thing is we have to store what happens. And if we take a look at what happens here, there are in total there are 6 cases. So you can have an interval that starts. And again, there are 2 subcases. The point is included or excluded. Then, obviously, you can have an interval that ends. Again, there are 2 subcases, excluded, included. And you can have a point or a hole. Point meaning it starts and immediately ends. And hole meaning it was true before, then it goes to false, and then goes to true again. So these are the 6 possible cases in this case. And then one thing that is very important, we want the interval set to be usable at any point. So we also have to know the value before the first change. So in this case, the first change is at 0, but we also need to know what is the value before 0. So we need one additional value, which is basically a Boolean, which tells you the value at negative infinity. And that's all there is to it. So let's take a look. one thing that's maybe interesting, this is kind of like a collection. It's kind of like a collection of values, but it is not exactly the same because we care not about the values itself, but we care about the spaces between the values. And that means that operations most of the time need to keep track of the predecessor value. That's one difference to collections. So let's take a look what operations would be useful. This is Scala code, but as I said, it doesn't really matter what programming languages it is. Scala is very nice to express these kind of things, but you can also do this in any other language. So it would be nice to have the ability to combine interval sets with an OR combination or AND. Then it would be nice to have the ability to negate. We've seen that already. And XOR kind of falls out of it. Because if you had those, you can make XOR. And then it would be nice to figure out if two interval sets intersect at all, if there's a single point which is true in both, or if they are subsets. So if one is true at all points of another one. So that's the operations that we're going to need. And, well, we might also need the ability to traverse over every single interval. I mean, just to print it, you need it, right? And that's basically what we would want to do regarding operations. This is, by the way, this exactly corresponds to something called the bool type class in a Scala library called algebra. It's a very common thing. It also exists in other languages like Haskell. And this has exactly those operations. They got names, and OR and complement is negation. And one additional thing we have here, we have a zero element. Zero element means the interval set that contains no values at all. And we have a one element, and the one element is the interval set which contains every single value. And we have all that, so at least we want to have all that, so we can implement this type class. By the way, that's one thing to note. You cannot have a bool type class for a single interval, because if you create the union of two intervals that do not overlap, then the result is no longer a single interval. So you cannot define a bool type class for that. But we can do it for an interval set because we have the ability to have two intervals in it. Okay, so let's take a look at the simple approach, the flat sorted array. This is kind of how it would look like. You have an object which contains just a single Boolean, which tells us whether the value is true or false at negative infinity. And we have two pointers, value and kind, which are basically pointers to arrays containing both the values and the kinds. So it looks like that basically. Here we have our numbers. 0, 1, 4, 5, 6, 10, like in the last example. And then we have a second array which contains the kinds, basically what exactly happens at the same position. So, and here we see how the intervals map into these arrays. So the interval 0 to 1 corresponds to these two elements and these two. And the interval 10 to infinity, we don't store infinity, obviously, we just say after the last value, we don't care anymore, it's just going to stay constant. And then, so this interval corresponds to just one entry. Yeah, so this is the simple approach. It has some disadvantages, but we will see a comparison later. And now we get to the a little bit more fancy approach, which is to use a tree. In this case, we know that our values are only 64-bit long. So we are using something called a trie, which is a prefix tree, meaning that the bits of the value determine exactly where a leaf goes into this tree. So this is how the tree looks. And again, we see that an interval corresponds to, well, in this case, 2 leaves. And in the other case, 10 to infinity, it corresponds to the last leaf in this case. And, well, the data structure that implements this tree is called interval trie. And, yeah, as I said, it works for 64-bit or less. With the additional limitation that you must be able to preserve order. You must be able to take this value and convert it into a 64-bit unsigned integer without changing the order. But this is possible for a double, except for not a number, which sucks anyway. So basically, you can convert a double to a long and back in basically 0 time, and that's how this basically works. And you can also use a Java time instant, which is one of the many ways to represent time currently in Java, up to millisecond precision and convert it into long and back. So basically, the idea is we're using a tree to store an ordered sequence of longs, and the data structure is, well, I started up with a data structure called long map, which is in the Scala collections library, and this in turn is implemented after a paper called Fast Mergeable Integer Maps by Okazaki. And Okazaki is very famous in functional programming circles. He has invented a very large number of interesting and very, very important data structures. So when you search long enough, you always get to Okazaki, basically. And so now the information, now basically we have the way to store the values. We are just going to use the tree. But now the interesting question is, what exactly do we store in a leaf? As we've seen in the previous case, there are 6 possible cases. So a leaf can be, well, it can start at a value, it can start after a value, and it can start and immediately end again. And now you might think that we need the other 3 cases as well, but it turns out that it's much better to not do that. Basically, what we do is we say if the value before the leaf is false, this is the meaning. And if the value before the leaf is true, we just basically reverse the meaning. And that way, we only need basically 3 possible values for each leaf, which has some big advantages. We'll see that later. This is again a little bit of Scala code. So the tree is a sealed class, and it can be only two different things, either a branch or a leaf. It's not a complex tree, it's just a very simple tree. And nodes have a prefix, which determines basically which area of the domain the branch is responsible for. They have a level, which tells you how high they are in the tree. The level can go from 0 to 63, and -1 we use for leaves. This is some obscure Java virtual machine stuff. Makes it useful to use this particular encoding. And the width of a branch, so basically the area for which a branch is responsible, is the level 2 to the power of the level. And then we have, now it's getting a little bit more interesting. We store a sign, which means it's a Boolean again, which means whether the value before the branch and after the branch is different. So if you start at false and you go to true, then the sign would be true. And if you start at true and go to false, sign would also be true. So a leaf node, this is how it looks in Scala, contains a prefix, a value at the position, and a sign which tells you whether it changes afterwards or whether it stays the same. And a branch node looks like that. We have a prefix, we have the level, and we have 2 children, always exactly 2 children. So it's basically a binary tree. And these children cannot be null. They can either be a leaf or a branch, but they cannot be null. And we have 1 bit of summary information, which is a sign, which is basically calculated as the left sign XOR the right sign. So if you look at the code, there's lots of bit twiddling in there. So let's take a look. There's one more thing. Basically, we have this entire tree structure, which consists only of branches or leaves. And then we need a way to store 1 more bit of information, which is whether the value at negative infinity is true or false. And to do that, we just wrap the entire tree in an object called interval tree, which has one additional bit of information, this below all value. And yeah, this is a value at negative infinity. And the pointer to the tree, Scala people will kill me for that, but basically this can be null if there is no change, basically. We'll see how it looks like. So this is how you would represent the interval that goes from negative infinity to positive infinity. Below all is true, and the tree is null. You'll never see this null from the outside, obviously. I'm not that bad, but it's more efficient to have a null than to have a certain value, which is a guard value. Basically, checking for null is extremely fast, and checking for comparing with a pointer is much slower. So we see this is the interval from negative infinity to infinity, and now if I take the empty interval, it looks pretty similar. The only difference is that below all is false, and the tree again is empty, which means there are no changes. There are no changes, so you don't need to have a tree, so there is no tree. This is a slightly more complex example from negative infinity to 10, excluded. Here we again have to store below all true, because yeah, it is defined at negative infinity. And then this is 10 encoded as unsigned long. Well, actually it's unsigned byte because I didn't want to have 64 digits here. And you see this is 10. And at the position it's true because it changes, and sign is also true because afterward it is false. And here we have the different things which kind of look similar. If you have just the value 10, nothing else, then add is true, meaning at 10 the interval is defined. There's a value inside, and sign is false, meaning that before and after 10 is the same value. And the last thing is another representation, basically it's flipped again. And this is something a little bit more funny. If I want to have an interval set that has basically, it is defined everywhere except there's a hole at 10. This is a typo, it should be 10 here. Then this is also just one leaf, which is a hole basically. It says this true means negate whatever is this. So here's true, that means at the value it is false. That means there's a hole in there. Okay, so what do I get from all this trickiness? Let's take a look. First of all, this is how a slightly bigger tree looks like. And as you can see, basically, one very nice property of a tree compared to a red-black tree or something is that the structure is completely determined by the values. In a red-black tree, you can have this situation that the structure of the tree will be different even though it contains the same values, because the order in which you insert the values matters. In a trie, you'll always have the same structure. And so that's one thing that we get. We have found a unique representation for our data, which means equality and hash code are free, basically. There is no code for it. Because all our classes are case classes, so they have a built-in equality and built-in hash code. And since we have a unique representation, we just need to compare them structurally to get, and it will always be correct. You could not do that for a red-black tree, for example, because a red-black tree, as I said, can have a different structure even though it contains the same values. So that's pretty neat. The best code is code that is not written. And let's take a look now how the operations work. So negation is, since everything is encoded relative to the value at negative infinity, negation is extremely trivial. Basically, we just take this flag below all and negate it. So negation of an entire interval set, it doesn't matter how many million intervals it contains, is an O of 1 operation. So it is basically one object allocation, that's it. So binary operations, which were kind of the point why we did the whole thing. This is a little bit more Scala code. I don't want to dwell on that too much, but the operations are all structured in the same way. Basically, you just have you try to reuse trees in intervals where the other tree is constant. So if you have a very complex tree in one side, but the other side is constant at that time, you can reuse the entire tree without even touching it, without even looking at it. And the only place where you sometimes have to actually look at the leaf values is if you have a collision, meaning you have two leaves which have the exact same value, and then you need to figure out some bit twiddling basically. And well, all the binary operations are structured in the same way. And this is a bit more detail about how the recursion works, but I got some nice picture that might be nicer. So as you can see, there's quite a lot of, well, bitmap operations. Here we are. So this is basically intersection. And as we can see, these are two trees, and we compute the intersection of them. And due to the fact that we can reuse large parts of each tree, we can basically, the only thing we have to do is to add an additional node on top, which reuses this part of the tree. So this is very efficient. I mean, in this example, it wouldn't matter very much because this tree is not very large, but imagine this was a tree with millions of intervals. It doesn't matter how big it is, you just have to put this thing on top, and that's it. That's called structural sharing, and it's basically the way that you can make functional data structures fast. It's used in Scala collections and also in immutable JS, and basically that's the only way to make functional data structures fast. So this is the OR operation. It's the same thing basically, except here in this case it's not quite as good. We have to create an additional leaf, an additional branch node. But as you can see, we are still reusing quite a bit of the original values. So that is basically, that are the operations. Sampling is taking just going into the tree and figuring out whether a value is true or false at that position. And to do that, we just have to keep track of the value before. So we have some additional operations which can compute whether two interval trees intersect or not. And the advantage of those is that they do not allocate any objects. So you can figure out whether two interval sets have a point in common without allocating a single object. So, okay, now we have seen all this complex stuff, so let's see what it's actually, what it gave us, whether all this effort was worth it. So I made two examples. Here are basically some intervals, and here's some other intervals which are a little bit shifted. And in total, we have 100,000 support points, meaning we have in total 50,000 intervals for both A and B. And now we compute the operation on them, which is the OR, and XOR, and negation. And here we can see this is 50,000 intervals, so it's not small. And we can see it takes about 3 milliseconds to do that operation. And it's about the same for all operations. And one thing we see that is negation. As I've seen, it's an O of 1 operation. So it actually takes just 8.5 nanoseconds on my machine. That's basically just allocating one object on JVM. So I mean, you can't get below that if you use functional data structures. So this is the interleaved case where the trees are basically in such a way that you cannot reuse big parts because they are interleaved. You have to go pretty deep into it before you can reuse leaves. And now another example is cutoff. I call it cutoff. There you have the same number of intervals, but one has a smaller stride than the other. Basically, one are very small intervals, the other is very big intervals. And in this case, you don't have to go all the way inside, but you can reuse big chunks. And as you can see, the performance is here way better again. So this is the payoff of structural sharing. There you see it. Now it's 33 microseconds to compute the union. And again, about the same to compute the intersection. And negation again, it would be the same. It doesn't matter. Okay, so the summary is basically everything inside of this data structure and the algorithms is immutable. There is not a single var, except in the iterators, which are non-functional by definition. And nevertheless, the performance is pretty good. But now, as we've seen, there's this other approach that we could take, basically just flat arrays. And for that, basically all binary operations that it can do are nothing more than basically merging sorted arrays. So let's take a look. Merging sorted arrays sounds like there's not much you can do. You just have to go through the arrays and merge them. But actually, that's not true. So one thing to note is that in many cases where you would use an interval sequence, the comparison is very expensive. So if you benchmark it, you notice that a single array element copy, so a single pointer copy, is 7 nanoseconds. A large array copy per element is ridiculously fast. It's 0.1 nanoseconds because the CPU can copy a huge chunk of memory in a single cycle. And comparing two rational numbers, which is what I wrote this for originally, takes 240 nanoseconds, which is basically an eternity in comparison. So the conclusion is, forget about the cost of copying array elements. Just ignore it. And only care about the number of comparisons that you have to do. And then if you do a little bit of literary research, you find that what you need to do, you need to merge two arrays, two sorted arrays, with a minimum number of comparisons. And this is described where else in The Art of Computer Programming by Donald Knuth. Some people might know it. And it's called the Wang-Ling algorithm. But this actually is pretty complex, and it does not degrade well in the case where you have a very cheap comparison. In an O of whatever sense, it can be improved because it's asymptotically optimal. But in the case where you have a very cheap comparison, it can be improved because you can have a simpler structure, basically. So I came up with another algorithm, which I think is also asymptotically optimal, but I'm too stupid to prove it, basically. But I think it's optimal, and it benchmarks the very cases and see that it's optimal. And it might actually be that this algorithm already exists and I just reinvented it, but I'm not sure. I haven't found it anywhere. So if somebody knows the name, I'll buy you a beer. Okay, so let's take a look what you would do. So these are two arrays which you want to merge, and in this case, you can see they are disjoint, meaning that if you are lucky and if you figure out that you have to compare this and this, you can merge these two with a single comparison and do this, basically. You probably won't find that, but that is the best case, basically. Then another thing, this is the worst case, that they are completely interleaved, the two arrays. So in this case, there's not much you can do. You basically just have to, in this case, you'll have the same performance as the normal algorithm that just picks one element from the top until you're done. So you have to do this, basically. And so what the algorithm should do is to, for every single comparison, imagine every single comparison costs you a lot. So you have to get the maximum value out of every single comparison. And how do we do that? I think it's nice to have a picture. So these are the two arrays, and we form a matrix. And now what we can do is basically figure out what comparison should I do in this case. If I do one comparison somewhere here, it also means, since they're both sorted, that I can fill out an entire area of this. So it's kind of obvious that what you have to do is you have to compare the middle element, so the center element of one array, with the center element of the other array. Because that's how you maximize the number of squares that you can fill out. So then what the algorithm does is basically just use this information and proceed. So you do a binary search, and then you do another binary search in the other array. And then there is some additional complexity because we're not just merging arrays, but we are also dealing with the kind of the interval border. But that's not very important. So this is how the operations actually look like. These are extremely mutable. I mean, we're talking about arrays. So basically, this is a thing that takes two arrays as input and has somewhere inside, it has a builder which creates another array. And after we're done, we're going to wrap that other array and pass it out. From the outside, it's still completely immutable, but inside it's using arrays, so it's immutable well, all over the place. But it doesn't matter because from the outside you can see it. And this is basically how the AND operation works. So you have this span of values inside the array A, and this is the value of B at that span. And if B is true, and you do an AND operation, AND true means you can just pass it through, and that's exactly what you do. If B is true, you just copy everything from A0 to A1, and if not, you do nothing. So that's everything. And as you can see, copy A basically will just invoke system array copy, and will be very efficient if A0 and A1 are far apart. If A0 is A1 minus 1, it won't matter very much. Will still be decent, but not very fast. But if this is a big chunk, then the CPU will just run through it. And well, from B is exactly the same except flipped. And then we have the case where we have to deal with the collision, but I don't want to dwell on that too much. So now the interesting part is we have two data structures. One is like by the book functional programming tree and so on. The other is array based. And let's see how they perform. So this is again the same case. We have two interval sets which are overlapping and slightly shifted. So this is the worst case again because we have to take one from the one from the other all the time. So and again, obviously the same number of intervals. And usually you would not use this data structure for smaller values like longs, but you would use it for heavy values like rational numbers. But in this case, we use longs because we want to have a fair comparison. So let's take a look. And as you can see, the performance is really not that bad. I mean, it's just a factor of 2 slower than the trees. I mean, all this effort with the trees, and you get just a factor of 2. Come on. So, and in this case, it's even a little bit faster. But one thing we can see is that negation is no longer an O of 1 operation. It's still pretty fast, 30 microseconds, but it's not basically free. So as you can see in this case, it's a little bit, this is the only place where it really hurts, kind of, the arrays. So now let's take a look at the cutoff example. The cutoff example is where the one collection contains very small intervals and the other one contains very large intervals. So you can always take a large number of intervals from one collection and put it into the result and so on. So that's where the trees should be a little bit better. And yeah, as you can see, it's quite a bit slower in this case, which kind of makes sense. And now we got the comparison. Who wins? For the interleaved case, we can see that the arrays, well, do a pretty good job, except for the negation operation, which is a factor of 10,000 slower, because obviously the one is an O over 1 operation and the other one is an O over n operation. And in the cutoff example, we can see that this is where the trees really pay for themselves. Because here, the trees can take in the tree case, you can take a huge subtree and move it over to the result without even looking at it. Whereas the array just has to copy it all. I mean, copying is pretty fast, but doing something is always more expensive than doing nothing. So yeah, that's what you get here. But well, I think it's still pretty decent what you get with the array, given that the array-based data structure is kind of a little bit more general. Okay, yeah, so that's basically the interesting result. Again, in both cases, this was a very big example, and it's very, very fast. I mean, if you do some day-to-day things, you'll probably never notice that it takes any time whatsoever. And also, it's pretty generic and kind of mathematical to use. So no builders, no mutability. You can basically just treat it like a atomic thing, which is way better than some data structures I've seen before in this. I've implemented for a very challenging situation, but I think it can also be useful in day-to-day things. I think I might actually port this to JavaScript at some point. Yeah, so that one more slide. If you want to use this, and if you're a Scala developer, so who's a Scala developer here? One, yeah, great. It does not seem to be a very Scala-heavy conference, but at least one, that's good. So this is in the Scala library called Spire, which is a basically library for algebra and math in the Scala language. And I also have a little repository where I basically play with this. But if you want to use it in production, then you would just use this library, which is very popular for the few people that do this kind of stuff. This library is very popular. It's kind of it's a type level project. So it's from the same people that do the CATS library. And yeah, you would just use that. And this is the presentation. It's basically, if you want to take a look at it. Okay, so that's it. Questions? Yep.
Do you use this library in some practical program, some projects, in your work or something?
Oh yeah, there is a basically I did the mission planning system for just all the way back. I did the mission planning system for this mission called Terza Tandem. That was written in C#, but in a very functional style. So it's actually using immutable data structures in C#. And there is a project to the next generation of this planning library at German Space Operations Center is using this, basically. I'm not there anymore. I joined a startup, but they are using this to implement the next generation of the planning software that they're using. And I also had some requests from some people in doing banking from London that they wanted me to give permission to use the library, which was not strictly necessary because it's an Apache library, but they nevertheless, for some reason, they wanted me to write, I hereby grant permission to blah, blah, blah. So some people are using it for whatever, high frequency trading. So no idea, really. Yeah.
So the benchmark numbers, are they averages, or is that just like a point sample?
This is a point sample, but I'm using a benchmarking library called Thyme, which is properly doing all the right things like warm up and sampling quite a few times and making sure that the JVM is in the right state. So it's not as accurate as JMH, but it gives you results after a minute, not after an hour. So JMH is perfect. It's so great regarding accuracy, but if you want to iterate, it just doesn't work. And this thing is, well, almost as accurate as JMH, but way faster. But these are, I mean, I'm pretty certain that if you would put it in JMH, you would get pretty much the same values. Yeah, so I guess no more questions. Thanks a lot.